Record, share. I want to get rid of this one. Okay, so a couple of things I want to say. First of all, I did give out a take-home quiz. Okay. I think that'll be good for everybody. If it's not good for you, let me know. If you have already got a great quiz grade, I would say that it's optional in a way. In other words, I'll use the quiz grade I have with OneDrop if you don't hand it in. I won't penalize you. Well, let's put it this way. If you don't hand it in, I'll use your 3 quiz grades and drop 1. If you do hand it in, I'll drop the lowest of the 4. You see what I'm saying? Okay. I think this one, because it's take home is probably going to be a good grade, which is why I'm giving it to you to try to build up your quiz grade if it's not high. Another thing I want to tell you about is the colloquium this Friday in my department is this thing about the McNair scholars. Ugh, heck. I just want to tell you about what this is. Well, I'm going to do it another way because this thing is not cooperating. So I don't know, have you ever heard of this program? Okay, so I just want to first is an information session about this McNair Scholars Program, which see if I can get to the information on it. I had this already, but of course it's not working. Now that I have your attention, nothing's going right here. Here we go. Try this one. Okay, so this is a program that you can apply to. And I'm going to click on the FAQs, and it's a scholarship program, and it's basically for people who are low income, first generation college students, or a member of one of these groups listed here. And I believe that they look for people that have a B or above average, 3.0, but I don't think it's impossible to get in if you don't have that average. What? Anyway, so I think this is a really great program, and if some of you fall into these categories that are listed, and you want to apply, you may want to find out more about the program first, and that's why I'm telling you that there's a colloquium tomorrow at 12 noon in Craigley 213. Where you can find out all about this program if you're interested. So it's a great program. I've known students in this program. It builds up their confidence. It gives them, they go to conferences. It's a really amazing program if you can get into it. So I would highly recommend it to some of you. Anyway, so anybody got a question about that? Sounds good. Good. All right. Anyway, so I'm just we're talking about Lewis structures. We're talking about drawing structures of simple molecules. And Paul, if you could have that conversation after class, it'd be better for me, So I think I went through the H2 molecule. All right. The H2 molecule is about the simplest molecule. And I talked about how, 2 hydrogen atoms, each with 1 electron, will come together and form. And sometimes people like to draw this with different colors, one from each, but that's kind of silly because these electrons are not distinguishable. And this is a shared pair of electrons. What do we call a shared pair of electrons? Anybody know? It's called a covalent bond, right? That's what a covalent bond is. And we draw it in the final Lewis structure. We use a line to represent that shared pair, that covalent bond. And so that would be, this is what we call the Lewis structure of the hydrogen molecule. And I can draw some of these just pretty easily. Like, for example, here's the ammonia molecule. Oh, and what it starts with, notice you have one electron on each hydrogen. So you start with the atom and you put the valence electrons around that atom. So NH3, you have 3 hydrogens and you have a nitrogen. Now, hydrogen, we know, has just 1 electron, and that, of course, is a valence electron. So there's 3 of them like that. But what about nitrogen? How many valence electrons does nitrogen have? So you take out your handy dandy periodic table. No. And you look in the numbers, the group numbers, okay? And it's in group 5A, which is also group 15, okay? That 5 there, either group 5A or 1, 5 or 15, is the number of valence electrons. So nitrogen has a Z of 7, but the first 2 electrons are in the filled N=1 shell. And so it's just the 5 other electrons, because nitrogen is 1s2, 2s2, 2p3. And these 5 electrons are the valence electrons. So we would take nitrogen and we would put these valence electrons around it, kind of in a, like that. And you could see that if you have a nitrogen that has these 5 electrons, and now I am going to use a different color for hydrogen, just to be clear, and each hydrogen contributes 1 electron, you have this nice looking structure. And what it does is it fills the shell in a way. It fills the N=1 shell for hydrogen. So each hydrogen has 2 electrons and a filled shell. Oops, I didn't. And also it does it for nitrogen. It gives it a filled N=2 shell, which is, filling in the next 2 electrons that it still needs over here in the 2p. So nitrogen has 8 electrons, which is a filled S and P shell, 2s and 2p in this case. And the hydrogens, by the way, we call that an octet, because octet from 8, right? And each hydrogen, so nitrogen has an octet, and the hydrogens each have a duet, right? There's 2 electrons, which is that filled N=1 shell. And when you write the Lewis structure, each of these pairs of electrons that's between 2 atoms becomes a bond. That's how we write it. So we would have a straight line, 3 straight lines, and then we would keep that pair that's only on nitrogen as 2 dots. And so again, these are shared pairs or bonds. And there are 3 of them, of course. And this guy here, this pair here, we call a lone pair. It is a non-bonding electron pair. It is associated only with the nitrogen, okay? So that thing with all the notations, this is the Lewis structure for NH3. Sometimes, if you might have learned in high school, sometimes you could represent that pair of electrons by a line. Some people teach it that way. This is a lone pair here. But I think it's clearer to actually have the 2 electrons like that. Okay, so that's our first couple of Lewis structures. And it points out this the business of having 8 electrons around most atoms, we call this the octet rule. The octet rule says that the stablest configuration for many atoms, especially the really common ones that we use in general chemistry, for many atoms is 8 electrons in the outer shell, which really means filled S and P subshells. So in other words, like 2p2, 2s2, 2p6, or 3s2, 3p6. Okay, and we've referred to this as an octet. So we're going to be doing a lot of Lewis structures of very simple molecules in the second period, and including hydrogen. Hydrogen, of course, doesn't go by the octet rule because it only wants 2 electrons to fill the n=1 shell. So I guess I should write that is the exception. Hydrogen wants, I'll put that in quotes, means for the stablest configuration, 2 electrons. Okay, so that's a big exception. And then we'll learn later on that there are elements in the third period and beyond which do not obey the octet rule, and we have some other things to talk about later. But for now, let's use this octet rule because it works pretty well for simple molecules. So if we were going to write the H2O molecule, water, okay, we have a hydrogen, another hydrogen, and now what's the valence electrons for oxygen? Group number 6A. The group number is the number of valence electrons. Well, not 16. You wouldn't do that. You have to take away the 10. Okay. So it's 6. So you go 1, 2, 3, 4, and then you would separate those two. So you'd have room for bonding. And then you would put it together like this. Again, I'm just going to use a different color to make it clear. Okay, so you have these 2 electrons associated with hydrogen. Hydrogen is good. It's got 2 electrons. Check. 2 electrons, check. And oxygen, 8 electrons, check. Okay, so what we do now is we replace those bonding pairs with lines, and oxygen has 2 lone pairs. These are not bonding electrons, they're non-bonding, but these are shared electron pairs or bonds, covalent bonds. Okay, all right. So there's a couple of things that can happen in Lewis theory. The very important one is that in Lewis theory, it allows for multiple bonds. So in other words, you can have a single bond or a double bond or a triple bond, at most a triple bond. So and that's the max, right? You can't have more than that. And so you could have a CO with a single bond, or you could have CO with a double bond, or CO, this is just an example, with a triple bond. And something that I'm just going to tell you now, we justify this a little bit more later, but if you have the same 2 atoms involved in a single, double, or a triple bond, the triple bond is the strongest. It's got the most electrons involved, so it's got the strongest, and it's also the shortest. Whereas this bond, the CO single bond, would be the weakest of the 3 and the longest. Okay, that's just something to keep in mind. So the thing about Lewis structures that makes it so powerful, even though it's so simple, is that if you can write the correct Lewis structure, so if you can sort of go by the guidelines I'm going to give you, if you can write a Lewis structure that has the following. the correct number of valence electrons. So you've got to count up all the available outermost electrons that are available for bonding. Remember, it's the outermost electrons that are responsible for reactivity. That's why they're involved in the bonding. So if you could write one that has the correct number of valence electrons, has octets for all atoms except hydrogen, and has duets for hydrogen, okay? And it uses all of those valence electrons, right? It could have lone pairs are allowed, so that's good. Lone pairs are allowed. If you can do this for a molecule, write that structure, there's a very good chance that that molecule exists. That's what's powerful about it. If you can do this, there's a good chance the molecule actually exists and is stable. And if you can't, then the chances are it's not stable, right? So I'm just going to say, and if not, then not. Then maybe it doesn't exist or it isn't stable, okay? There are exceptions, there's lots of exceptions, but it's pretty good for a lot of simple molecules. But the thing is, you cannot randomly write a Lewis structure. I mean, you might be able to land on a correct Lewis structure if you get lucky, but it's very hard to do randomly. So I'm just going to tell you that from the outset. It's hard to get the correct Lewis structure if you handle this randomly. And a lot of times students are tempted to just, write the Lewis structure for CO2, and they just they don't bother with the rules, they don't count up the valence electrons, and it comes out completely wrong. So I'm going to struggle with you and to try to convince you that you really have to go by these rules, because the rules are based on the chemistry. Okay, so you really must use these simple rules to get to the right answer. I mean, you might get lucky, but you might not, okay? And so I have a handout that I gave you last time, chapter 7, chemical bonding. Geometry is later. We're working on chemical bonding right now. And this activity 1 is about writing Lewis structures, simple Lewis structures for molecules. And I write it here. It's very tempting to try to write a Lewis structure without using the guidelines. Unfortunately, that often leads you to the wrong answer, okay? So here's the set of steps to get it right. Okay, so I'm going to go through 3 examples, and then I have an activity where you can do some Lewis structures, and I will come around and help you. Okay, so let's start with this POBr3. So the very first thing you have to do is you have to count the valence electrons for each atom. You have to add them up. This is not an ion, so I don't have to tell you how to deal with ions right now. Just count up the valence electrons. And I recommend that you do not start by writing an electron configuration. You simply use the periodic table, okay? If it's in group 1A, it's 1 valence electron. If it's in group 4A, it's 4 valence electrons. If it's group 5A, it's 5. Just look at the group number. If you want to use the 13, 14, 15, 16, 17, that's fine. Just subtract the 10, right? So P, where's P on the periodic table? And what is its number of valence electrons? It's in group 5, 5A or 15. So this is a valence here is 5. What about oxygen? 6. What about bromine? 7. So it's 3 times 7 because there's 3 of them. So there is a total of 5 plus 6 plus 3 times 7, which is 32 electrons, 32 valence electrons to play with in this Lewis structure. So what we do next is we divide it in half and we come up with 16 pairs. Okay, so there's 16 things that are going to either be bonds or going to be lone pairs, but we don't know where to put them yet. In fact, we don't even know how these atoms are arranged, because the way this looks, it looks like the oxygen is in between a P and a Br, but that's not the way it is. Okay, so that's number 2. Decide on the skeletal structure of the molecule. The skeletal structure is simply how the atoms are linked together. And you need your electronegativity chart, which was the top page. If you don't have this handout from Tuesday, you should come and get it, because that's where this is that I'm talking about. Does anyone need one of these? Okay, we go to the second page. There's a giant, most of the periodic table. It doesn't have the rare gases, but it has the electronegativities of all of these elements. And that is what you have to use to decide on a skeletal structure. The central atom should have the lowest electronegativity. So you want to look up the electronegativities of all of these things. So what's the electronegativity of P? 2.1. We have 3.5 for oxygen and 2.8 for bromine. So there's no problem here. We got P in the middle. Okay, and now, you know, these are simple molecules. Generally, there'll be one atom in the middle, but you'll see later on in the handout that we do that they could be, you know, a linear molecule where there are like 2 atoms in the middle. But right, we're going to do the easiest way we can. We're going to put an O and 3 BRs. Okay, so that's it. We put our P with the lowest electronegativity in the middle. Why do you think the element with the lowest electronegativity should go in the middle? Think about what electronegativity is, though, right? Electronegativity is a desire, in a way, to pull electron density towards itself. The one in the middle is sharing with all 4. You wouldn't put an atom in the middle that's really electron grabby, because they don't like to share. It's like a, you know, one of those toddlers that doesn't want to share the toy. Okay, so that's why the least electronegative one usually goes in the middle. There are exceptions, of course. All right, so that's step 2. We did that. We did 1. Now, this is very important. Draw single bonds from the central to the terminal atoms, terminal or outer atoms. So these are the terminal or outer atoms, okay? And you just want to draw single lines, 1, 2, 3, 4, and you want to count them, right? Because we know we have 16 pairs that we have to use up. If we only use 15, that Lewis structure is wrong. If we use 17, that Lewis structure is wrong. You see what I'm saying? You got to really use the right number of electrons. Okay, so that's 1, 2, 3, 4. We did that. Okay, the next step. Place lone pairs, non-bonding electrons, on outer atoms until each has a full octet, aka the rare gas configuration. Okay, so I have 16 minus 4 is 12 pairs left. So I'm just going to start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I use them all. If there are any, so 4 is done. If there are any remaining electron pairs, place them on the central atom, but there aren't, so I don't have to do that. So I'm finished with 5. And now is a very important step. Review the structures. It's like before you press that you want your credit card to be debited when you're buying something from Amazon. You want to review your order, make sure that everything is all good. You have an octet. So you have, this makes, you understand that that makes an octet. Each line is 2 electrons, 2, 4, 6, 8. You have an octet here. You have an octet here. You have an octet here. What about the P in the middle? Does it have an octet? 4 bonds, each has 2 electrons. That's 8 electrons. So we reviewed this structure. Does a central atom have 8 electrons? Yes. Do all atoms have 8 electrons? Yes. So this is a Lewis structure. I don't want to write it again without the circles, but you know, it would be, oh, I guess I don't have to. There you go. That's the Lewis structure. All octets. So that's done. This is the Lewis structure for POBr3. Any questions yet? Okay, now we're going to do another one, IF2 plus. So how many valence electrons do we have here? What does I have? How many? It's in group 7. 7 electrons, 7 valence electrons. Okay, and fluorine. So fluorine has 7. So we have 2 times 7 plus 7. What about this plus charge here? What do you think that means? All right, so but let's add the so far we have 21, right? Because we have 2 fluorines and 1 iodine. But because of the positive charge, that means that this molecule or this ion has 1 less electron than it should have. That's why it has a positive charge. Okay? So if there's a positive charge here, you have to subtract 1 electron for each positive charge. So we have 21 electrons minus 1, that's 20. In Lewis theory, you have to have an even number to make a number of pairs. So if you have an odd number, something's probably wrong. Okay. Like I wouldn't ask you to do a Lewis structure for NO2 because that would be an odd number, and you can't do that within the bounds of Lewis theory. Like I said, there are some exceptions. What is going on here? All right. So there's 10 pairs. Okay, so we're done with number 1. And now the skeletal structure. So what is going to be the skeletal structure? What atom is going to be in the middle here? Yes. Because it has the lowest electronegativity from the chart. Electronegativity of I is 2.5. Of fluorine is 4. Okay, so I is going to go in the middle. And then we're going to have the 2 F's on the side. And we're done with number 2. Number 3. Draw single bonds. So we have 10 pairs. We're going to use 2 of them up right away. We have 8 left. Place lone pairs on outer atoms until each has a full octet. So we use up 1, 2, 3, 4, 5, 6, 7, 8. Wait, something's wrong here. 9. Oh, it's 10 pairs. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we have 2 left, so they go in the middle. 9, 10. So we used all 10 pairs. There were 2 remaining. There were, so we did that. We put them on the central atom. So that's done. Now, do we have full octets on all of these atoms? How many electrons on this one? 8. You count it, right? They both get that bond. 2, 4, 6, 8, 2, 4, 6, 8, 8, 8. So there are full octets. Okay, so this, the only little thing we have to do to finish this up is put a bracket that indicates that it is a positive ion. So we put a bracket and a plus charge. And that Lewis structure is done. Okay. Any questions about that? All right, so next I'm good. Sorry, yeah. So I'd like to work on HCN next, hydrocyanic acid. And we have to count up the valence electrons. So valence electrons for hydrogen is 1. What's it for carbon? 4. So group 4A. Nitrogen is 5. So this is 10 electrons, 10 valence electrons. So that's 5 pairs. Okay. All right. So now let's think about so we did 1, and now we have to decide on the skeletal structure. All right. So our rule says to put the atom with the lowest electronegativity in the center, but there is an exception to that. What happens with the atoms here? Which one has the lowest electronegativity? Can I ever put hydrogen in the center of a molecule? No. Hydrogen can never be in the center. Hold on. Yes, it would be the next lowest. The reason for that is because it can only bond to one other atom. Because it can only accommodate 2 electrons in that N=1 shell. So that said, the carbon has an electronegativity of, what is it, 2.5. So even though hydrogen has the lowest electronegativity, it can't be in the center. The electronegativity of nitrogen is 3. So carbon is in the center. So that is the skeletal structure. Now we have 5 pairs. We're going to start by putting 1, 2. Then where am I going to put the lone pairs next? Around the end. 3, 4, 5. And I'm done. Okay, so I did that. Place lone pairs. There's none left. This is where it's very important to review the structure. What is wrong with this structure? What are we checking for? Yeah. That's right. Carbon does not have an octet. So this is when you make multiple bonds. You do not make multiple bonds because you feel like it. You make multiple bonds when you need to give something an octet that doesn't have it. So I'm going to take this pair here and make a double bond out of it. So now I will have this. Okay. And now what's the situation? So I'm going to take another one. Come on, pen, you could do it. There. Okay, so now you see that I have a duet here for hydrogen. I have 2 electrons in that bond. I have 2, 4, 6 from the bonds on the right, 8 from the bond on the left. I have an octet. For the nitrogen, 2 from the lone pair, and then I have 6 from the bonds. And so this is the Lewis structure for HCN. So, please take that to heart, honestly. The business about not making multiple bonds until you have to, because I see students making bonds here. They have 4 bonds. They have students do the craziest things. Just go by the rules and you'll be fine. All right. So let's do this activity. Um, yeah. Just see how far you can get, you know? Work on it, talk to your friends. You have it in front of you. And I have some things to say when we're done. I'll go over it and but I want you to spend some time on this. Start by counting your valence electrons. I didn't do a negative ion, but see this SO3 2 minus. Let's just look at this. If you're counting the valence electrons here, you'll have sulfur. How many valence electrons for sulfur? And oxygen, and there's 3 of them. That's 24 total. And then you have to add 2 for the 2 negative charges that we have here. So it would be 24 plus 2 is 26. So that's 13 pairs. So that's how you handle negative ions. I have a take-home quiz here to give out. Did you all get it? Sure you get it. Everyone know what they're doing? pairs of electrons. 10. 10 of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only have 18 electrons. 9 pairs. Wrong pairs. Did not follow the rules. Start again. You're good with the skeletal structure, but when you count those electrons, you gotta be careful. Right. Okay, I don't know why you made it involved. Don't make them involved. And you only need them if you don't want to. What is easy? That's not a computer. Over here. Wait. Yeah. One there. Oh, that's a bond. That. Yeah, did you figure that out? Yeah. Somebody tell me your way. You have to follow. Right. You have 2, 4, 6, 8, 10, 12, 14, 16, or pairs. You want to do 4 by 8 pairs. 8 pairs. Right. Right. Oh, fine. All right, we're gonna do ozone together. All right, O3.
Oh, yeah.
O3. I'm seeing every mistake that, you know, that students make, and I don't want this to go any further, so. You have to, please stop, please. So this O3 is ozone, by the way. So we start with O, 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 and that's the way I feel as I'm walking around. O, O, O. All right. How many valence electrons in each O? Does everyone agree? That's not the problem. 6 times 3 is 18. So how many pairs? Right. 9 pairs. That means 9 of these or those, right? You have a bond or a lone pair. You can only have 9. What's the first thing you do? Single bonds between atoms. All right. Now, where am I going to put the others? You know, you might just don't talk right now. You can talk after I'm done. So on the outer ones, 1, 2, right? Now you go 3, 4, 5. Where do I put the next ones? On the other outer ones, 6, 7, 8. And what do I do with the last one? In the middle. Look at the instructions. That is exactly what it says for you to do. Now, do you have octets? Which one doesn't have an octet? No octet. Okay. So what am I going to do to get an octet? So I can't just do this. I can't just do this, right? Why can't I do that? Why can't I do that? Because then how many pairs would I have then? 10. And I'm not allowed to do that. So I have to borrow one. I have to, if I take one from here and make it, what does that do? Does that help me? No, because then I would lose one of the pairs on the middle oxygen. And the problem is the middle oxygen is the one that needs the extra electrons. So I would take one from the side. And so I would end up just copy everything over. Now I have 2 lone pairs on the right. Okay, so you cannot draw double bonds at will. You can't just add in electrons. You can't have more than an octet on an atom that's in the second period. There are some exceptions later, as I mentioned. So that's ozone right there. You gotta force yourself to look at the rules. Use the rules. See, I'll write a very short version of the rules because they're a little detailed. So 1, count the valence electrons. Divide by 2 for the number of pairs. Single bonds between atoms. Oh, I guess I should have put least electronegative atom in the center. single bonds between atoms, lone pairs on outer atoms. 5, lone pairs on the central atom, if there are any left over. And you can't go above the number of pairs that you have that from the valence electrons. Finally, you have to review the structure and check for octets. And you want to make double or triple bonds only as needed. Okay? All right, see if you can work on that some more. Okay, are you okay with that now? Yeah. It's good to make that mistake today. Doubt that your geometry is pretty much. In other words, this is actually linear model. But that's not, we haven't learned that yet. Learn that next. Yes, question. The both all the way to H and H. Always need, because H has to be on the end. Oh, I have to be on the new. Okay. Well, that doesn't necessarily mean it's linear. You learn about that next time. Yes. I did. I did the two ends in the middle and the H is on one either side. Yeah. Oh, two. Another one. Expand your balance. Rules that I've taught. Anyway.
Yeah.
Structure, but, right, not what we like school. I would just go back and wait for the outside.
Yeah. Yeah.
Are you still working on this? Good. Fine. You want to show me what you've done? Anybody? Well, we want me. So let's find out 2 lines of interest. Yes. I know you're looking for in the edge. That means like. I don't.
You got 6 pairs.
Yeah. That's the 905.
So there's 5. So there's 5 pairs. So 3. 4, 5.
Yeah, we have 5. Right. So then brackets.
So it's like this.
Oh, okay, well, this is not a print skill. On again. It's crazy. Oh,
Yeah.
and all the ages are okay.
We did that here. Yeah. Yeah.
This one I would like to end. And some change. And all. So. But the end is H2, but the 2 ends in the middle and the H is on the end. I was, yes, that's kind of, yeah. Hi. Yeah. How many you guys? Six?
Oh, yeah.
There's no way to put them there.
Like negative, positive.
It's not done.
Yeah, so it's gonna be one of the next little things.
Less.
Yeah, wait. 4.4, and then 15. Oh, yeah, now you're that. I'm better than Oh, in other words, you know, you understand. Oh, that's what I mean. Yeah. That one, I think I. Yeah, yeah. Oh, wait. But you heard that. No, I just have. I like your one better. All right, I have to move on pretty soon. I'm gonna go over these. All right, let me go over these. Yeah, okay.
I've noticed going around the room that there are a few things that people are doing wrong. Okay, and I want to nip them right here in the bud. You never put lone pairs on hydrogen. Why? Because all hydrogen can have is one single bond. That's it. And hydrogen is never in the middle. Because if it's in the middle, that means that it's bonded to two things. And it can't bond to two things. So even though it has the lowest electronegativity, it's going to be an outer atom. All right, let me go through these. Okay. N2, we have 5 valence electrons times 2, that's 10, or 5 pairs. So we start by putting 1, 2, 3, 4, 5. So now we're going to make a double bond because we have to, because there is no octet here. So when we go to review the structure, we fail, right? So we take one of these, and then we'll have this. Is that done? The nitrogen on the right is good, but the nitrogen on the left is not. So what are you going to do now? Yeah, and I'm not going to take this pair because then I'd be losing a set of electrons there. So I will take one of those. So that's N2. O3 I already did. Well, let me go over it again. What the hell? If I could erase it, that'd be really helpful. I know. So oxygen times 3, that's 6 times 3 is 18. That's 9 pairs. So 1, 2, 3, 4, 5. Notice I'm going to the outer atoms. 6, 7, 8. And then I have one left over. One pair goes to the middle. But my middle atom is not satisfied. It doesn't have an octet. So I have to make a double bond. And now I have octets. 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. Okay, so that's done. Okay, let's do SO3. I explained that S will go in the middle because it has the lowest electronegativity. We have 13 pairs here because of the 2 electrons that we added because of this -2 charge. So we go single bonds, 1, 2, 3, outer atoms first, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have another one. I put it in the center, 13. Check for octets. 2, 4, 6. I'm good on this oxygen. I'm good on this sulfur. I'm good. I have 8 electrons on everything. All I have to do is put a bracket with my charge, and I can erase the checks because it's all fine. All right, ClO3, I was with the back group there when they figured out that the Cl had to go in the middle because it has the lowest electronegativity. But let's count up the electrons. Cl, how many? 7, it's in group 7A. 3 times oxygen is group 6. And then I have to add 1 because of the negative charge here. That gets an extra electron. So that's 7 plus 18 plus 1. Yeah. Arithmetic, yeah. 26 divided by 2 is 13 pairs. So single bonds, 1, 2, 3. No, it doesn't matter. But later on, we'll learn about what the geometries of these molecules really are and how you figure that out. That's next week. All right, 1, 2, 3, 4, 5, 6. Go away. 7, 8, 9, 10, 11, 12, 13, and last one goes in the middle. And you could see I have octets on all of these as well. 2, 4, 6, 8, etc. There's 8 electrons on every one of these. So I just have to finish by putting my negative charge like that.
Writing the list structure, we always have to, and there's a negative or positive charge.
You're supposed to put a bracket. Yeah, it's. See this stupid thing? What am I supposed to do with this, huh? I mean, honestly, go away. It's loading. Oh, shut up. What? I close all the windows before I start. Oh, I didn't close this though. I know. It's just like, give me a break. I know it's a first world problem. Look, it still won't go away. Oh, finally, the X came up. Okay. Great. All right. Yay. All right, what's next here? Oh, so now, of course, it put the SO2 on top of the NO. So we have NO2 minus. Okay. So nitrogen has the lower electronegativity. So we have 2 O's. 5, I should add this up. 5 plus 2 times 6 plus 1 for the extra negative. That's 9 pairs. So I'm just going to draw it straight. What the heck? Even though it's not really right, but later we'll learn about that. So we have 1, 2 single bonds, 3, 4, 5, 6, 7, 8, 9. What do we have to do here? That's right. I have to make a double bond.
So what would be the right way?
That's the right way.
So
That what? Oh, no, that's not for today. Okay, so this asks, would you expect NH bonds in N2H2? Oh, we didn't do N2H2 yet. N, N, H, H. I know this is not the skeletal structure that some of you had, but this is the one I had wanted, so I'm going to do it. 2 times 5 plus 2, right? 2 electrons for each hydrogen, 1 for each, I mean. And so that's 12, so that's 6 pairs. 1, 2, 3, 4, 5, 6. So now what? Yeah, you need a double bond because the nitrogen on the left there is lacking in a pair of electrons, so you end up with this. Okay, so this is a Lewis structure. Well, what this question is asking is if the NH bond is polar. Remember, polar, you have to have an electronegativity difference of 0.5 or greater. So the electronegativity of nitrogen is it 3.0 or 3.0? And the electronegativity of hydrogen is 2.1. The difference is 0.9. So it is polar, which is to say that each of those NHs has an arrow, a dipole pointing from the hydrogen to the nitrogen like that. Later on, we'll learn that those cancel, but that's not for today. I think I skipped a few of these, right? I didn't do CH4. So carbon is 4 electrons, hydrogen is one each, 4 times 1, so 4 plus 4 is 8. That's 4 pairs. The carbon has to go in the center because hydrogens can't go in the center. 1, 2, 3, 4, that's it. We have octet on the carbon. We have duets on each hydrogen. That's correct. What about this other one? C2H2. This is an interesting molecule. This is acetylene. You have an acetylene torch. This is the fuel. Here's the skeletal structure. And we have 2 times 4 plus 2, 10 electrons, 5 pairs. 1, 2, 3, 4, 5. So how am I going to make, what am I going to do? Those carbons are each deficient. Yes. Yeah, but he says put a triple bond. He's right, but I never do a triple bond all at once. I do it one at a time. Right? I can see now that I'm still in trouble. So I'm going to have to make another, because sometimes, it's hard to tell that far in advance. But if you're good at chess, maybe you're good at just putting in the triple bond, You're good at chess?
Not really. I saw that.
Yeah,
I did it. Likewise, but
yeah.
it's not really good at the same time, but
Right. What I didn't, there is a question about the CH bonds in CH4. Is the CH bond in CH4 methane? Yeah, because if you look at the electronegativity of the carbon, it's 2.5. And for hydrogen, it's 2.1. That difference is 0.4. That's not 0.5. It's too small, so it's non-polar. Okay. All right. Well, there's something else I want to talk to you about, as you might imagine. And this, if we look at ozone again, so this is what we ended up with. So O3, we started out like this. We had 9 pairs. We went 1, 2, 3, 4, 5, 6, 7, 8, and then we put the last one in the middle. And then we realized that we had to take and make a double bond. So I could make that one, but why couldn't I do this? If I was at this stage, and I'm sure some of you did it this way, that instead of picking the right oxygen to take the lone pair and make a double bond, maybe you picked the left oxygen and did it. Okay, and so you could actually end up with these 2 structures. We call these 2 structures resonance structures or resonance forms. Sometimes they're called resonance hybrids. And we put this funny double arrow in between, okay? And now here's the thing. What it means is that neither one of these structures on its own is correct. That you actually need to have a little bit of each in order to describe ozone, okay? That what you kind of really have is something more like this. You have sort of like 1.5 bonds in between. Do you see sort of how this structure is in between these 2 structures? And what it is that the electrons of that double bond, right? Those 2, that electron pair of the double bond is actually spread out over all 3 oxygens. All three oxygen nuclei are sharing those two electrons. So you might ask, well, how do they know that? Well, we do a lot of things called spectroscopy. We saw a little bit of that with line spectra of atoms, but there are all kinds of physical things about molecules that can be deduced from looking at how they interact with light. And one thing that scientists have proven is that the two bonds, this bond and this bond in O3, in ozone, are absolutely equivalent. They have the same length, they have the same strength. There is no experimental evidence that one bond is different from the other. So that implies that you do have some kind of spreading out of that second pair of electrons, that last pair, the one that's part of this double bond here, that's actually spread out. We say that it is delocalized. I don't think I'm sharing the screen anymore, but oh well, we're live here. Let me try doing that. So what's really going on is you have this delocalization of that electron pair throughout the whole molecule. And you need really both resonance forms to fully describe ozone. You have a very similar situation for the NO2 minus. If you remember, the structure that was correct for that one was this. Very similar, except you have a bracket with a negative. But really, you would have two different looks to it. One that puts the double bond on the right and one that puts the double bond on the left. And there is resonance here. These are resonance forms where this double bond of these electrons are delocalized, spread out over all three of those atoms. Yeah. So if you have a molecule or a polyatomic ion, so for a polyatomic ion, you know that molecule is carrying extra charge. The molecule, is carrying either extra, negative, or positive charges. So you might ask the question, where is that charge? What atom is that charge all on one atom? Is it a couple of different atoms that shares that positive or that negative charge? So it's sort of like, where is the positive or negative charge located on the atom? Okay, so there's a method that we use to determine the charge on each atom in a molecule, or where that charge is. Even in a neutral molecule, you could have one atom could be more positive and another one could be more negative. It's possible. So even in molecules which are not ions, right, the charge may not be evenly distributed. So we have this thing called formal charge. And formal charge is just a way of assigning charge within a molecule. And it's very helpful for chemical reactions, because a lot of times chemical reactions are initiated where a positive charge, a positive part of one molecule attacks a negative part of another molecule. That would be called an electrophilic attack. These are things you learn about in organic chemistry. But what I want to do is show you how you calculate formal charges. So I'm just going to look at this NO2 minus again and do this example for you. So here's here's one Lewis structure, one resonance form. Okay. By the way, on the quiz, I think since we're just covering this, what I'd like you to do, on the back, number 6, you could just cross out B. You're not gonna do B. Okay. So I'm going to show you how to count up formal charges here. So formal charges, like I said, a way of counting up, sort of figuring out which electrons are on which atoms. And so basically what we do is we add up the electrons on a given atom. So we're going to add up the electrons on a given atom. And we're going to compare this to the number of valence electrons that atom started out with. If it has more electrons in the molecule than it did as an atom, then we say it has a negative formal charge. And the number of more negatives that it has, that's the number of the formal charge. I'll do an example. If it has fewer electrons in the molecule, so when it's in the molecule, then it in the molecule than it did as an atom, then it will have a positive formal charge. All right, so let's just look at this structure here. Let's look at, we'll call this oxygen 1 and we'll call this oxygen 2. So oxygen number 1. How many electrons are associated with this oxygen? Now, this is what we do. The lone pairs are entirely associated with the atom that they are on. That makes sense, right? Lone pairs only are associated with the atom they are on. Okay. Bonds, we split them in half. 1 electron for each atom in the bond. Okay, so oxygen number 1, from the lone pairs, how many electrons does it have? Now we're counting up single electrons here. So how many electrons on that atom? 1, 2, 3, 4, 6 from lone pairs. How about bonds? How many atoms does it have from bonds? Well, wait, remember now we're breaking this bond in half, and we get 1 electron goes that way, 1 electron goes that way. So there's 1 electron from 1 single bond, right? Okay, I don't know what that came from. So we have 6 plus 1 is 7 electrons on oxygen number 1. Okay, what are the valence electrons for oxygen? Is 6. So it has 1 more electron now in the molecule. Another way to do this is to take the valence electrons and subtract the current electrons. So it would be 6 minus 7, right? So it has 1 more electron now, so we would have a formal charge of -1. Or you could do 6 minus 7 is -1. And that tells you that this oxygen on the left here has a formal charge of -1. Okay? This is oxygen number 1. Let's do oxygen number 2. Let me rewrite this down. This is what we have so far. Okay. So let's do oxygen number 2. How many electrons from lone pairs? All right, 4 electrons from lone pairs, because there are 2 lone pairs. All right. How many electrons from bonds? That's right. So now we have a double bond that we're breaking in half. Remember, there's 2 electrons from each of those. So we have 1 electron from each going to either side. So we have 2 electrons from the 1 double bond. So you add up 4 plus 2 and you get 6. And what is the valence electrons for oxygen? Right. 6 minus 6 equals 0. You have a formal charge of 0. Finally, let's do this nitrogen, okay? Electrons from lone pairs, how many? 2. Right, there's just a single lone pair. Electrons from bonds. Yeah, you're breaking this one in half, you get 1 from that, and then you have 2 from breaking the double bond. So you add 2 and 5, so 2 and 3. That's 5 electrons. And what is the valence for nitrogen? Group 5A, 5. So the formal charge on the nitrogen is 0. So I could write it this way. It's supposed to be a 0. So that shows the formal charges. So you see you have a polyatomic ion with a -1 charge. And that -1 charge is on this oxygen here. Right, but now, and these two have 0. If you add up the formal charge on each atom of a molecule or a polyatomic ion, you should get the overall charge. Yeah.
So nitrogen gets, so I think it's still nitrogen.
You have to count up the electrons. You mentally divide the bonds in half. So 1 electron from there, 2, 3, 4, 5. So 5 electrons on this nitrogen, and nitrogen has 5 valence electrons. And so it's the same. It doesn't have more electrons and it doesn't have fewer electrons. If it has more, it would have a negative formal charge.
So is this a way to check ourselves with the charge, if there's a charge on the?
Well, right, if you did this and you got -1, -2, and 1, and you add up, that's -3, that's -2, that's the wrong charge. That's true, that's a way of doing it, but yeah, it's a hard way to do it, but yeah. The other thing is that, of course, we have the other resonance form, which is this. And And this oxygen here is equivalent to this one here. You can see they each have three lone pairs and one single bond. So they would have the same formal charge. So this would have a formal charge of -1. And these guys would have formal charges of 0.
The oxygen to the right.
Oh, I do, you're right. Good job, wow. So gotcha right there. Yeah. Because there'd be 1, 2, 3, 4, and then half of each of those bonds, 5, 6. Oh. Oh my God, I can't erase it. Yeah. So you actually, when you take organic chemistry, or very shortly, even before you, even in this course, a lot of times you won't see the lone pairs written at all. You'll see it written like this. And you would have to assume what those pairs are there. And whenever you see an O with a single bond, you know it has a formal charge of -1, which is important to know if you're trying to figure out reactivity. Because like I said, something negative will attack something positive because there's a attraction of unlike charges. Okay, so I would like you to get started on this thing, and we have just not that long, but we have a little time. And I have this it won't do it. That's not it. Oh my God. Turn to the next page after that activity 2. It's not this. It won't go to where I want it to go. It's the one that has the CSN thing. Yeah. This thing. So just see how far you could get with this. I would just like you to just try to calculate, just do this part, calculate the formal charge. We haven't learned about which would be stable or not stable. That's not what I'm after. Let's just do formal charge.
One more.
Whatever you do is get credit. Just a quiz.
Yeah, but cross out 6B.
Alright.
But it could be extra credit if you do it.
I need those gotchas.
Yeah.
Thank you.
But then when people come and tell me about things from like a year ago. Oh, you want me a gotcha from not 2016.
Can I get one from that too?
One of these is yours. I gotta sign it. It's not valid.
So how does
until
that
I-
even work?
Yeah, what do we have to do? Hand
You
it
know
to
what? I'm not telling you again. Go read it on the syllabus. It's very clear.
You absolutely cracked me up.
I needed
Do you love how I pulled out my mom voice to the chitty chatties in the back of the room?
Thank you.
Did
Like,
you hear
hey,
me?
look, I put his name on both.
It's quite all right, my friend. I
Here you
get
go,
it.
David.
No, you're fine.
David.
David,
Thank you.
he's brain dead today.
Oh, so am I.
Since I'm turning this into pictures of this.
I did post the solutions. All right, it's Thursday. I gotta get out of here.
Before you go, where exactly did you go over question one for the Liz? I must have been a little.
That's a long time ago.
Yeah, I must have been.
I don't know when I did it exactly.
I don't remember how exactly that worked.